Greetings, dearies. And today we are going to be looking at probability. And without wasting time, we'll start by understanding what probability is, okay? So it says by definition that probability is the measure of the likelihood of an event occurring or not occurring. Likelihood or chance is a measure of the chance of an event happening or not happening, right?
Yes.
For example, what are the chances that tomorrow it will rain? What are the chances that a football team A will win the game? What are the chances that a certain person will pass the subject or fail it? Okay.
Yes.
Now that's probability. And whenever you hear probability, there is a formula that we will use to calculate probability. So if A is an event, then to calculate the probability of event A happening, you have to find number of times that A is occurring or is appearing,
Yes.
right? Over
Yes.
the total number in the sample space, okay?
Okay.
All right. So P of A, it means probability of A. I was now defining the things you see in the formula, okay? I'll give you an example of what is happening here, right? Then
Yes.
N of A means number of elements in A or number of times A is appearing. Then here, number of all possible outcomes. That's what you have from this formula, right?
Okay.
So,
Yes.
to give an example of that, let's say we have a box. And in this box, 1, 2, 3, 4. Right. What color is this that I used here in the first circles that you see?
Blue.
Blue. Oh, you're not colorblind. Let's use another one. Then 1, 2, and 3, right?
Yes.
Now, if I ask you if B represents blue, right? And
Okay.
G represents green, okay?
Yes.
If I ask you to calculate the probability of picking blue, right? According to this formula, it is the number of circles that are blue over the total number of circles, right?
Yes.
So what do you think is the probability here of picking blue?
It's 4/7.
So there are 4 blue circles over a total of 7, right?
Yes.
So that's what this formula is talking about, okay? 4 over 7. Are we there?
Yes.
All right. Then this sign that you see here, it's intersection, and at times you find it replaced by the word and. Are we there?
Yes.
So here we are discussing probability of A and B occurring, probability of A intersect B, or probability of A and B, okay?
Yes.
So here you'll be discussing a probability that both events A and B will occur, all right?
Yes.
All right. This language we are talking about is borrowed from sets. Can I give you the background of it?
Yes.
If you have a universal set, something like this, let's say you have a set of numbers 1, 2, 3, 4, 5, 6, 7, and 8, right?
Yes.
Let's say this is a mother set. You have a very big container, and in that container, you have a certain group A, which is taking the numbers 2, 4, 6, okay?
Yes.
Then you have a certain set again, taking 2, 3, 5, 7. Are we there?
Yes.
So here, if I ask you A and B, or let me write it this way, and B, right?
Yes.
It means I want elements that are found in both A and B. That's what this means, okay?
Yes.
So which elements do you see?
It's 2.
2. Is there another one? That's the only one, right?
Yes.
So if I now ask you probability of A and B, right? I'll now want number of elements that are there in A and B over the total number of elements. Are you there?
Yes.
So the total number of elements, it's elements that are there in the bigger container. Are we good?
Yes.
It's like in a class, you have people who do maths, you have people who do physics, you have people who do maths and physics, right? but
Yes.
overally you have a class. Are you there?
Yes.
So here, let's say this A is representing the ones for maths and the B representing the ones for physics. So this 2 is representing a learner who does maths and physics. Do you get the picture?
Yes.
But all of them are learners in the same class. Okay. So now, what will be the probability now? How many times do we have, or how many learners do we have in A and B?
7.
Now,
2.
in A and B, look at this. This is the set
Yes.
representing
Oh,
A and B.
it's 1.
It's 1. We only
Yes.
have 1, right? One number appearing in both, right?
Yes.
Okay. Then we need now the total number of learners. 1, 2, 3, 4, 5, 6, 7, 8. So we have a total of 8. Do you get the picture now?
Yes.
Aha. So that's what A and B means. These are events that can occur at the same time. Elements that you found in A and they are also in B. Okay.
Yes.
Then we also have probability of A or B. Okay. Now,
Yes.
if I want to explain A or B using the same example above, you have A. So this one, it will take elements. What will happen is you are taking elements that are in either A or B or both. Okay.
Yes.
But what you do is you just avoid repeating the intersection. So let's say in A, do you see that I have elements 2? Let me start with 2. I have 2, I have a 4, and I have 6, right?
Yes.
I have exhausted all elements that are in A. I need to take again elements in B, but I don't repeat those which are appearing in both. So 2 is already appearing, right?
Yes.
So the other number we don't have is 3, another one is 5, and another one is 7. This one is A or B. It takes either A or B or both. So you just don't repeat the ones that are appearing in both sets. Okay?
Okay.
Okay. So now, if I ask you now for the probability of A or B, you're now talking about the number of elements that are in A or B over the total number of elements available. So here you have 1, 2, 3, 4, 5, 6. So it is 6 over 8. Are you getting the picture?
Yes.
All right. So that is probability, the definition and the formula that we'll be using. I've just shown you how it works. All right. Are we fine?
Yes.
Then
Yes.
in our definition here, we said probability is the measure of the likelihood of an event. Event. You see this word? Event.
Yes.
We have different types of events. So we have types of events. Types
Events.
of events. Are you with me?
Yes.
Okay. So we have what we call mutually exclusive events. When we speak of mutually exclusive events, these are events with no outcomes in common. Okay?
Okay. Yes.
Which means there is no intersection. Remember here we said, when we defined intersection using the example down here, we said there are elements that are there in common, right?
Yes.
But do you see that if A was like this, 2, 4, 6, right?
Yes.
And let's say B was like this, 5, 7. Do you see that you don't have elements in common?
Yes.
You see that the intersection will be empty. There's nothing. You don't have any elements in common, right?
Yes.
That's what happens when we are talking about mutually exclusive events. These events, they cannot occur simultaneously. So it means the chance, right,
Yes.
of the intersection occurring is 0. Are you there?
Yes. Yes.
So whenever you now go to the exam and you see the sentence, are the events mutually exclusive? Your job, you're trying to find out, is the probability of the intersection or end? Because we said intersection means end, right? Probability of A and B should be 0. So if it happens to be 0, you conclude that the events are mutually exclusive, okay?
Yes.
So an example I have for that is an event that a number is even and the same number is odd. You see, it cannot happen, isn't it?
Yes.
Because an even number, by definition, it's a number that is divisible by 2 without leaving a remainder, okay?
Yes.
And on the other hand, an odd number is a number that is not divisible by 2 without leaving a remainder. So you cannot have a single number that satisfies the condition for even and odd at the same time, right?
Yes.
So it could not intersect. Another example, how many sides are there on a coin?
2.
What are the names?
Tail and head.
Tail and head, right? Is it possible that you toss a coin and you get both tail and head?
No.
Good. I was afraid you would say, what if it sits on a crack? Then no, that is not tail and head. Okay, so it is not possible to get that intersection. Are we good?
Yes.
So on this one, mark this part. It is very important. It will lead to the answers of other questions that will come across. All right?
Yes.
Then we have what we call complementary events. So two mutually exclusive events that together contain all outcomes in the sample space. So here, we'll write this formula. So you see on the notation, sometimes they put this prime. You see it, right?
Yes.
Another one is some they put the bar on top. Okay?
Okay.
Some
Yes.
they just say not A. Are we there? So what will happen is probability of A plus probability of not A, the answer will be 1. Okay?
Yes.
You will remember this. We will be using these things. For now, we are just laying the foundation, trying to bring back the knowledge of lower grades. Okay?
Yes. Okay.
Then we have what we call independent events. So these two events A and B are independent if the outcomes of the first event does not influence the outcome of the second event, right?
Yes.
So an example, e.g. for independent event, I want to create a picture of what we are talking about. Remember, pictures make it easy to understand these things, right?
Yes.
I have a container, 1, 2, 3, 4, right?
Okay.
That's blue. Then let me put red. I hope it's red indeed. Okay, 1, 2, 3, right?
Yes.
Now, if you look at the example I gave here, it says tossing a coin and getting a head and do it again and get a head, neither outcome influences the other. When you toss a coin and get a head the first time, right?
Yes. Yes.
If you go and toss the coin for the second time, it does not affect the outcome of the second time, okay?
Yes.
Or another way is something that we have a further discussion on. You see here, what is the probability of picking blue?
It's 4/7. 7.
Over 7.
7.
The other twin, do you understand where the 7 is coming from?
Yes.
So we have 4 blue, then we count all the circles in the container, right?
Yes.
Now, so this is the chance of picking the first time. Let's say someone picks, okay? Are we there?
Yes.
Then they replace again. So what is the chance of picking the second time? If this was first time, if you look now in the container, what is the probability of picking blue again?
4/7.
4/7. So the event that happened the first time has no effect on the second event. So the events are independent. Okay?
Yes.
All right. Then we now have dependent events. Dependent events. Two events, C and D, are independent if the outcome of one event influences the outcome of the other. So the example says, if a box contains, let me make that box so that you actually see what is happening. That's a bed box, but it's a box. Let's say it's about to be torn. Now, contains 4 green. So let's put green as it is. 1, 2, 3, and 4, right? 4 green.
Yes.
And 3 red. 1, 2, and 3, right?
Yes.
So when you withdraw 1 red ball, without replacement, this reduces the number of choices when you decide to draw the second time. So let's do what this sentence is saying, right?
Yes.
You see here, what is the probability, let's say for the first time, what is the probability of picking red?
3/7.
3/7, right?
Yes.
Now, for the second time, let's say when someone picked the red ball, they kept it in the pocket, right?
Yes.
Now, what do you think is the probability of picking red again?
2/6.
2/6,
6.
because now the container has 6, right?
Yes.
But do you see that the chances of picking red were better before we took out the other red one, right?
Yes.
So the chances, okay, the event of picking red the first time has influence on picking red again. Because if you look into the container, do you see that you now have higher chances of picking green than red, right?
Yes.
So the first outcome affects or influences the second one. Do you see it?
Yes.
Then we conclude that the events are dependent. Are we fine?
Yes.
All right. So that's theory. Then in probability, we have rules. So please don't break the rules of maths. The police will come for us. Rules of probability. Rules of probability. Now, in the rules of probability, I said here, let P be success probability, the probability of success, and the Q represent the probability of failure, right?
Okay.
This which you are looking at, the first one, it says the probability of success is an answer that should be between 0 and 1 inclusively. Are we there?
Yes.
So you cannot get an answer 5 in an exam and you start enjoying, celebrating, saying, I did it. It's a lie. Okay?
Yes.
So all the answers of probability should be between 0 and 1 inclusively. By that I mean, if you get a probability 0, it means you are certain that the event will not occur. Okay?
Yes.
For example, the probability that tomorrow is Sunday, given that today is it's Wednesday, right? The probability that tomorrow is Sunday, it's 0. Okay?
Yes.
Then the event, if the probability is 1, we are certain that the event will occur. Are we good?
Yes.
All right. So that's what it means. Then another one, this one we saw it. We saw that probability of success plus probability of failure, the answer is 1. This is the same as saying probability of A happening plus probability of A not happening, the answer is 1. Remember complementary events?
Yes.
Aha. That's exactly what we are talking about. Okay?
Okay. No.
Huh? Are you there? Look, can I give you an example, okay, in a diagram way?
Yes.
Okay, let's do this. 1, 2, then different color. 1, 2, 3, right?
Yes. Yes.
Let's say from this diagram that you're looking at, right?
Yes.
The diagram you're looking at, let's say success is picking red. Are we there?
Okay.
What is probability of picking red here?
2/5.
2/5, right?
Yes.
Okay. Now, it means if you have not picked red, you have failed. That's what we are talking about, right?
Yes.
So if you pick blue, it means according to us, you have failed. That's probability of the failure, right?
Yeah.
Okay. So what is the probability of blue? Do you agree that it's the same as just saying probability of not red?
Oh, yes.
Do you see the picture?
Yes.
And what is the answer? Because if you are not picking red, obviously you are now picking blue. Do you see it?
Yes.
Okay. And our success, we said it's red. Now, what is the probability of picking blue?
3/5.
3/5. Now, check this number. If you do probability of red plus probability of not red, which is probability of blue, by the way, if you do 2
Yes.
over 5 plus 3 over 5, what do you get?
1.
1.
Yes.
Okay. So do you
Yes.
realize that it's probability of success now plus probability of failure, right?
Yes.
Aha, that's what I meant. Is it okay now?
Okay, yes.
Good. Can I move on?
Yes.
So the idea is I'm trying to give all the theory in this first part and see what comes next with examples, okay?
Yes.
Then here it says the addition rule for any two events. If you are given any two events, there's a reason why we have this word, these words, any two events. You'll see when we move to the next. Now, look at this. If I am to put a Venn diagram, something that we'll discuss at length later, let's say I have two circles, and these circles are intersecting like this. Okay, let me put them nicely. Now, then I close this container, close them inside like that, right? If this is A
Yes.
and this is B, this portion here is A and B, okay?
Yes.
So probability of A or B is equals to probability of A, but when you say A, it means you are following this circle. Do you see it's blue, right?
Yes.
Okay. Then
Okay.
plus probability of B, again, when you follow B, it is this green one. Do you see that there's a section that is appearing in both?
Yes.
Okay, you see it, right?
Yes.
So immediately when I did A, I included the portion. When I do B, I am repeating. So I have to say minus the intersection. Do you get it?
Yes.
So this is the addition rule. Probability of A or B is the same as saying probability of A plus probability of B minus probability of A intersect B, because at that point you would have included it already, right?
Yes.
Okay. Then what happens if events are not just any events but are mutually exclusive? Okay. So the same rule,
Yes.
addition rule, right? But
Yes.
for mutually exclusive events. Exclusive events. There on top, we said for any events, right?
Yes.
So the formula for probability of A or B in this case, it will be probability of A, sorry, it will be probability of A plus probability of B, right?
Yes.
But remember that if events are mutually exclusive, the chances of intersection, the probability of intersection is equals to what? We spoke about it.
Probability of intersection.
It will be equals to what? For mutually exclusive events,
0.
it will be 0, right?
Yes.
So do you see that that formula will be minus 0? The one you know will have a 0 in the end, right?
Yes.
So it simply means the actual formula for mutually exclusive events is simply probability of A or B is equals to probability of A plus probability of B. Just like that, it will end here. Okay?
Yes.
In terms of diagrams, it means you will have circle for A and a circle for B, but the two are not joined. There is no intersection. Are you following?
Yes.
You don't have intersection. Are you getting me now?
Yes.
Okay, done. Then we have another part, and in this part, we have what we call the complementary event. We spoke about it already, where we said probability of A plus probability of not A, we said it's equals to 1, right?
Yes.
So this one is covered. So if I give you one of these, you can find the other one, okay?
Yes.
Then now we have this, the product rule for independent events. If events are independent, probability of A and B will be equals to probability of A times probability of B. This is what happens if events are independent. Do you understand me?
Yes.
So if it happens that you are given probability of A and B, and you know probability of A, and you know probability of B, then you multiply these two, A and B. Then your answer turns out to be the same as the probability of A and B. You conclude that the events are independent. Okay?
Yes.
So let's quickly write something important because there are questions they normally ask. Important. So to prove number one, if you're asked to prove
Yes.
that, if you're asked number one to prove that events are mutually exclusive, right?
Yes.
If you're asked to prove that events are mutually exclusive, then check if probability of A and B is 0. Okay? That's what you'll be looking for. Are you with me?
Yes.
All right. Then on number 2, if you're asked to prove that events are independent, right?
Yes.
Are independent, then check if probability. So we said this part, A and B, right?
Yes.
Then probability of A and B is equals to probability of A times probability of B. So whenever you're asked to prove whether events are mutually exclusive or not, you are checking if probability of A and B is 0. If events are independent, you are checking if probability of A and B is equals to probability of A times probability of B. Those are things you'll be looking at. Okay?
Yes.
Okay, that's something. Then we have this part done. Then another one, important again, as we do this probability, the word end, if you come across the word end, it means multiplication or means addition.
Yes.
So in this session, we managed to define the terms, what is probability. Then after, we discussed the types of events and we discussed the rules of probability, right?
Yes.
Okay. Now we end on this part, then we come back and apply and continue with the other piece. All right.
Yes.
Is it fine? Any questions before I close this?
No. No.
Okay. Thank you, guys.